the last thing that we talked about last time was I/O-bound processes versus CPU-bound processes. So I/O-bound processes are processes that do a lot of I/O. They request I/O very frequently. CPU processes are the processes that do a lot of computation, actual CPU computation. And I/O-bound processes are the more interactive, user-interactive processes. And when we get to scheduling, we will see how the system treats each of these two kinds of processes differently, and it will be trying to in fact, the system will be, the scheduler will be giving more time to I/O-bound processes. But we will understand that when we get to scheduling. Now, some systems may have a medium-term scheduler, and that medium-term scheduler may take some processes off the ready queue and store them on the disk. Why? There are two possible reasons for doing this. One reason is that memory is full and it's trying to free up some memory. Because remember, the ready queue is an operating system data structure that is in memory. So that's one good reason for doing this. Another good reason for doing this is achieving a better balance between CPU processes, CPU-bound processes, and I/O-bound processes. So in this case, the medium-term scheduler will take one process that is, after it completes its time quantum, it will swap it out, which means it will put it on disk, and then it will be a partially executed process. And later on, eventually it will swap it in, so it will, when there is enough memory, it will put it on the ready queue. But it's the medium-term scheduler is not something that we need to worry much about. Like I said last time, our focus is on the short-term scheduler or the CPU scheduler, the scheduler that looks at the ready queue and picks one process per CPU from the ready queue. Okay. Now we will talk about context switching. So context switching is a concept that we have covered in previous lectures. I don't know if I have used the term context switching then or not, but context switching is what the work that the system, the kernel, has to do when it switches context. And what is switching context? Changing the process that is running on the CPU. So if we have process number 1 running on the CPU, so this is the, should remember that, process number 1 running on the CPU, then the time quantum of this process expires, so the kernel takes control, takes possession of the CPU. Now the kernel will have to give the CPU to process another process, which is process number 2. Let's call it process number 2. Now, the work that the kernel does here includes context switching, which is saving the state of the process that lost the CPU and restoring the state of the process that is going to get the CPU. And we talked about this last time. What do we mean by the state when we say saving the state of the process that lost the CPU?
The contents of the registers that might have been used by that process.
Yeah, saving the values of the registers, and what else? There's something important that we need to save in addition to the CPU registers. Yeah?
Program counter?
Yeah, exactly, the program counter. So that the system knows where the process left off, so that it can pick up from where it left off. This is what we need to save. This is something that the system needs to save so that it can use it when process number 1 later on gets the CPU. So sometime in the future, process number 1 will get the CPU again. And now the system needs to know where to start that process. So it must start it from where it got interrupted. So process number one, this is the code for process number one, and it got interrupted here. Then this is where the system needs to restart the process, and it must save the program counter for that process in order to do this. And it also must save the values of the CPU registers. So this is what we call context switching, switching context on the CPU from P1 to P2. Now the time that is taken in context switching depends on two important factors: the design of the operating system itself and the hardware. So the design of the operating system, so there are lots of updates that the system will have to make when it switches context from one process to another. It will have to update many system data structures, kernel data structures. And what data structures, that depends on how the system is designed. So that's why the time for context switching is dependent on the design of the operating system. It's also dependent on the hardware, because what do you do in context switching? So this is, this is memory, this is the CPU, and it has some registers, A, B, etc. Now in context switching, so this is process control block 1, and this is process control block 2, and they both are in the kernel address space. So process control blocks are kernel data structures, and they are in the kernel address space. So when with this example, P1 is losing the CPU, so we need to store the values of the CPU registers into the process control block for process number 1, and we need to load the values of the CPU registers from the process control block of process number 2. So there will be copying of data from CPU to memory and from memory to CPU. And obviously the speed of this will depend on the speed of the memory system. Faster memory system will give us faster transfer of data between memory and CPU. Now other factors are, the processor may have, some processors or some instruction sets may have a single instruction that allows you to copy all registers with one instruction that just stores the values of all registers in memory, and another instruction that reloads the values of all registers from memory into the CPU. So if there is such an instruction exists on the processor, that will speed up context switching. So that's why context switching is hardware dependent. In general, context switching takes a few milliseconds. Well, I think this is milliseconds is such a long time. But when we say a few milliseconds, how many machine cycles are these? 1 millisecond is how many machine cycles?
A lot. Is that a 1 gigahertz?
Well, assume that the machine is 1 gigahertz. Yeah, assume it's a 1 gigahertz machine.
It's 1,000. It should be 1,000, right?
1,000? So if it's 1 gigahertz, then each cycle is how many seconds?
1 nanosecond.
1 nanosecond. So if it's 1 gigahertz machine, then one cycle
It's 1 million.
is 1 nanosecond, or 1 nanosecond per cycle, which means that 1 millisecond is a million cycles. So it's important to have a sense of how long or how short these numbers are. So it's not short. It's not as short as it looks. We're talking about millions of machine cycles. Okay. And all the machines these days are, the clock speeds. All the clock speeds now are in the gigahertz range, which means that a machine cycle is in the nanosecond or a fraction of a nanosecond range. Okay, so let's talk about mobile systems. So here, the idea here is that on mobile systems, there are some resource limitations, including battery life and the amount of memory. A mobile system has limited memory, and battery life is important. And because of this, the system cannot afford running too many processes in the background. So we know the concept of a background and foreground. Foreground is the process that is on the display and you are interacting with. But when you are interacting with one process, there are multiple processes that are running in the background, like your browser or your email, for example. The email server is running in the background and it's receiving messages, or your WhatsApp, for example. When you are not on WhatsApp or you are running some other application, then an application like WhatsApp that is receiving messages is doing that in the background. So not all processes can be run in the background. It has to be a process that is that uses limited resources in order to be allowed by the system to run in the background. Why? Because the resources are limited. So on each system, iOS or Android has its own limitations on background processes.